Let's jump right back into some more examples of power series and determining what the radius of convergence and the interval of convergence is. So for this example, if we're looking at the series from n equals 1 to infinity, root n over 8 to the n times x plus 6 to the nth power. First thing we want to figure out is where is this centered at? So where is this centered at? Remember, we're looking for x minus a to the nth power. We're trying to figure out what is the a value at which this is centered at. So a couple ways to do that. You could take the x plus 6 and set it equal to 0. Figure out that this is at x equals -6. You could just utilize the visual here, and obviously it's the opposite of 6 since it's x minus a in the definition for a power series. So we are definitely centered at, I'm going to actually write it down here. We are centered at x equals -6. And for a visual, if it helps, you could draw a number line and say, okay, so here's -6. And we're trying to figure out how far right to the left and to the right that we can actually go from 6. What is our radius of convergence? And to do that, after we figured out where we're centered at, the next thing we're going to do is we're going to apply either a root test or a ratio test and come up with that radius of convergence. So let's go ahead and say let L be equal to, I'm going to go ratio here. So ratio test utilizing the ratio test here, limit as n approaches infinity of, we're going to have the square root of n plus 1 times x plus 6 to the n plus 1 over 8 to the n plus 1 times 8 to the n over the square root of n times x plus 6 to the nth power. All of that in absolute value. Keep going, simplify this down. We're going to have the limit as n approaches infinity of, I'm going to bring my roots together, so I have the square root of n plus 1 over the square root of n. Go ahead and bring my 8 to the n over 8 to the n plus 1. And I have my x plus 6 to the n plus 1 over x plus 6 to the n. Now you don't have to write this step, I just am showing this so that you can see the canceling directly in ratio form. You could jump right here to this next step where we actually have the absolute value of the square root of 1 plus 1 over n times 1 over 8 times x plus 6. Let's actually put that x plus 6 over the 8. This is all in absolute value. So I'm going to go ahead, I'm going to go out this direction now. So I can go ahead and we're taking the limit as n approaches infinity. So this portion of, undo. This portion of the limit is a constant relative to n. So I can pull that all the way out. It is an absolute value, so I can pull it all the way out. 8, of course, in absolute value is just 8, but x plus 6, x is variable, so we'll keep that in absolute value. And then we're just taking the limit as n approaches infinity of 1 plus 1 over n. But that, of course, is going to, this piece of it's going to approach 0. That's just going to be the square root of 1. And I end up with x plus 6 in absolute value over 8. Okay? That's what my limit is. Now, remember what the ratio test says. The ratio test says that if this limit is less than 1, we have convergence. It's actually absolute convergence. Okay? So that's what the ratio test says. So this limit that we just found right here, if this is less than 1, we will have convergence. Remember, our whole goal here is to figure out what values of x will give us convergence. So we will have absolute convergence when the absolute value of x plus 6 over 8 is less than 1. And that's what we're going to work with to come up with our interval of convergence and our radius of convergence. So let's actually, I'm going to bring that up here to the top so I have a little more space. And I'm going to say, okay, so the absolute value of x plus 6, so this series will converge. When the absolute value of x plus 6 over 8 is less than 1. Okay, well remember, we're trying to figure out where around -6 this will converge. We're centered at -6. We're trying to figure out where will that converge. Well, let's just multiply both sides by 8 here, and we find that x plus 6 is less than 8. That tells me my radius of convergence. That's giving me my radius now that I've isolated the x minus a. Just back to our definition for radius of convergence, it's when x minus a is less than some value r. So that's coming out of just our definition for radius of convergence. So what is our r here? Well, we know here that our radius of convergence now is 8. So our radius of convergence is 8. That much we know. Radius of convergence is 8, meaning we can go 8 to the right and 8 to the left of -6. So where would that put me? Well, you could do that in the inequality. We'll do it in the inequality too, but you could also do it on the visual. If you add 8 here, of course, you're going to end up over here at 2. And if you subtract 8, going 8 in the opposite direction, you're going to end up back here at -14. So what we know right now is that our series will converge for all the values in between -14 and 2. So we have like a start to our interval of convergence. We don't know yet what's going to happen at the endpoints. So we do still have to test the endpoints before we can put a bracket or a parenthesis here, before we can talk about if they're included or not. So we still have to test our endpoints, but once we've tested our endpoints, we can determine our interval of convergence. So we'll test our endpoints as our next and final step, but we do know what the radius of convergence is, and we know the interior of the interval of convergence. We know that this series will absolutely converge between -14 and 2. So we can plug in -14 and anything in between -14 to +2. So that's our radius of convergence. So let's come down here now and let's actually do our testing. So let's test those endpoints for convergence. So what we know right now is we've got -14 to 2. We just don't know if these are going to be, I'm going to just put red parentheses around here. We just don't know if this is what we don't know. I'll put parentheses and brackets. We're not sure yet, so we got to figure that out. So we know we're between -14 and 2, but we got to test each of those. So we test -14. So if I plug -14 actually into my series, let's see if I can get my series all on the same page here. So there was my series. So my series is from n equals 1 to infinity, square root of n over 8 to the n. So we're going to plug that in to the actual series. So this is going to become the series of the square root of n over 8 to the n times -14 plus 6 to the n. And we're going to examine and figure out, does that guy converge from n equals 1 to infinity? So let's figure out if that converges or not. Well, just take a look at what that ends up being. That ends up being the series from n equals 1 to infinity, root n over 8 to the n times -8 to the n. But we could write that as -1 to the n times 8 to the n. And so this series is actually, when we plug in -14, n equals 1 to infinity of -1 to the n times the square root of n. Now, simple divergence test here. If I take the limit as n approaches infinity of the absolute value of those terms right there, of a sub n, that would be the limit as n approaches infinity of the square root of n. That would be infinite. That's definitely not 0. And with the switch, this oscillates, not only is it infinity, but it oscillates between positive and negative infinity, and obviously diverges by the divergence test. Okay? So we're utilizing what we found in infinite series for our test here to show that this guy diverges. So what that means is I can actually now come back up to my interval of convergence, and I cannot, this guy at -14, this diverges. So I definitely do not want to include it. So now I can come back here where it had that red question mark. I can say this has to be an open interval at -14. I have to do the same thing at 2. So now we take x equals 2. and we plug that in. And if I plug in 2, n equals 1 to infinity of the square root of n over 8 to the n, well, when I plug in 2, I get 2 plus 6 to the n. Well, that's just exactly equal to the square root of n over 8 to the n times 8 to the n from n equals 1 to infinity. Obviously, those two are going to cancel, and this results in just the series n equals 1 to infinity of the square root of n. And this one, we don't even need the absolute value. This one, we can simply say that the limit as n approaches infinity of the square root of n equals infinity, which is not 0 and must diverge by the divergence test. So this guy's definitely diverging when we try to plug in that endpoint as well. So it turns out this is a series, a power series, where on the interval of convergence, both of the endpoints give us divergence, so we cannot include either of them. So this diverges at this endpoint as well, and so we come back here to our endpoints where we were testing, and we say this guy must also be open interval. So our interval of convergence is from negative 14 to 2. So when we come back to the actual series that we were looking at and we were saying, well, where will this converge? This will only converge in between. We can actually come in now for our endpoints if we want a graphical visual here, and we can write that. And so this series right here has a radius of convergence that is equal to 8, a finite value, and an interval of convergence, and I will use IOC for to abbreviate interval of convergence, and an interval of convergence from negative 14 to 2, non-inclusive of those endpoints. We had to check those. What happens is the ratio test, I'm going to zoom out so we can have that all on one screen. What happens is the radius, that's going to get pretty small to get it all on one screen. The radius of convergence ends up telling us where we have absolute convergence, and so we're absolutely convergent. The series is absolutely convergent in between negative 14 and 2. And then what happens is we have the possibility of conditional convergence at the endpoints, but this particular series that we're looking at, both endpoints diverged, and so they weren't even, not only were they not absolutely convergent, but they weren't even conditionally convergent. So we had divergence at the two endpoints. All right. So there, it's all on one. Sorry, we're getting a little bit of some other examples on the same page too, or on the same screen, but trying to show it all here. So we applied the ratio test, so it determined where it was centered at, determine where the series is centered at, apply the root ratio test and the theory behind root and ratio test for where those limits will converge when they're less than 1. And then we figured out what the potential interval of convergence was and then tested the endpoints so that we could have, we could show whether they converged at the endpoints or not. All right, I want to try to get 2 more examples on this video for you. So here is another example. So here we've got a series from n equals 1 to infinity of n to the n and x to the n. And what I would say on this particular example is that this lends itself nicely with those powers to the root test. I'm jumping ahead a little bit. We should first decide where this is centered at. And so I look at this and I see that x right there. That's like an x minus 0 to the n. And so this is definitely centered at x equals 0. And so when we do our number line, if we want a visual, we're thinking, okay, so we're centered at x equals 0. And then we can run the root test to determine what that actual radius of convergence is. So we can define our L. Sorry, I didn't mean to change that to red. So we can define our L to be the limit as n approaches infinity. And this time, we're going to take the absolute value, we're going to take the nth root or 1 over nth root of the absolute value of n to the n, x to the n, which is going to give me the limit as n approaches infinity of n times the absolute value of x. I pulled the n out of the absolute value simply because n is positive, so I don't need to have it inside the absolute value, but the x I do. But notice what happens here. As n goes to infinity, this is going to become infinity times x, or infinite. This is infinite, which this is obliterated x. The index right there in the root test here has now obliterated my x value. And it turns out that this means that by the root test, this guy is always, always, always greater. This is greater than 1 always. Or another way to think of that is for, it doesn't matter what x is. This is for all values of x. This guy is greater than 1, which by the ratio or ratio test, by the root test, this means divergence. So what that means for us is that our actual radius of convergence, this is saying that this series, regardless of what we put in for x, it is not going to converge ever. It's always going to be divergent for all values of x, except for this one value of x right here where we are centered. If we were to actually plug 0 into this series, by the way, it becomes 0, right? 0 minus 0, 0. We're going to end up at just a series of 0. It does, our infinite series here, our power series, will always converge right where they're centered, that one point. So this means that my radius of convergence is actually equal to 0, and my interval of convergence is the most restrictive interval it can be. It's only at a, only at 0. Okay, this is the a value. So it is only at a. This series will only converge when we have x equals 0. That's the only place it will converge. Okay? So this is one of the extreme cases. You have your two extreme cases, your radius being infinite, meaning it will always converge, or in this case, it will always diverge, your other extreme. Okay? The series diverges for every value of x except for 0. Okay, let's get one more example into this video. I know we can do it, even if it makes the video a little long. I think I want to wrap up with this video. So let's do this example here. If we have this series from k equals 1 to infinity of 4x minus 3 to the k over k times 4 to the k. And a couple of things. First thing we want to figure out is where we centered. So where is this centered? And remember, to find out where we're centered, we got to have x minus a, in this case k, or to the n, whatever the index is. So where are we centered at? We're centered at a, where x minus a to the k, x minus a raised to the k is part of the power series. So a couple of things here. We could first manipulate this series, and I might do that. I see that 4 on the x right there, and I might want to clean this up a little bit. It'll help us with some later work. So one way to do it is just to look here, and I see that 4, and I think I'm just going to factor that 4 out. So I'm going to pull the 4 out. I'm going to have a 4 to the k, and when I do that, what gets left behind here is x minus 3/4 to the k. Now, when I factored it out, of course, I have that k right there as well, because I factored it all the way out of that with that exponent on it. So I pulled it outside the parentheses. And then down here on the bottom, I have k times 4 to the k. That's one nice reason to pull it all the way out, because now I could say, oh, well, check that out. That's just, those cancel. And this is just x minus 3/4 to the k over k. So that simplifies, that's just one way to do it, just simplify the series. So here we're simplifying the series. Another way to do it, if you want to figure out where you're centered at, is just to take your 4x minus 3 that is raised to the k here, set that equal to 0, and you would find that x equals 3/4. And that's going to tell you what your a value is. So that's another way to do it without simplifying the series. But because I'm going to be working with this series in a ratio and a root test, or ratio or root test, actually, I think I'm going to go ratio on this one. I just think simplifying it within the series itself is a nice way to go too. Okay, so either way, we figure out where we're centered at. This particular case, we come out and we are centered at 3/4. And now we just need to figure out how far can we go to the left and the right and still have convergence. Okay, or is it that we can't go at all? Maybe the radius is 0. So let's go ahead and get in there with our ratio test. So now let's apply the ratio test. I'm going to apply it to the simplified version, but you can apply the ratio test and get to the same result with the original. So I'm going to apply the ratio test limit as k approaches infinity of x minus 3/4 to the k plus 1 over k plus 1 times k over x minus 3/4 to the k. And I'm going to continue to simplify that down, and I'm going to end up with the limit as k approaches infinity. I have just the absolute value of x minus 3/4. It's to just the first power. So I'm just going to drop the power and just write it as x minus 3/4. And then I have that multiplied by k over k plus 1. Now the x minus 3/4 is a constant in terms of this limit, so I can pull that all the way out, x minus 3/4, and then just take the limit as k approaches infinity of k over k plus 1. But that's got to be, if I want to just use my degree of p of k equals degree of q of k, that's got to just be equal to 1. So those two lead coefficients, the degrees are the same, so it's just the two lead coefficients. So this ends up being just x minus 3/4. Technically, we are times 1. I'm going to erase that, but we are multiplied by 1. Okay? I won't erase it. I'll just write it on I'll just write the next line. So then we've got x minus 3/4 in absolute value. So that's what my limit is equal to. But remember, again, remembering what our ratio and our root test say, this has to be less than 1. So the root test tells me that we have convergence, converges when we didn't do root test. We did ratio, but the root does the same thing. Converges when this limit is less than 1. So if I want convergence, I know that this absolute value of x minus 3/4 has to be less than 1. Now that, because I already have isolated it, that's my x minus a. Oops, I'm sorry, I lost my screen there for a second. That means that this is my x minus a, has to be less than 1. X minus a, that means that's what my radius is, since I've already isolated the 3/4. Now, if I had been working with this original series, and I at this point have 4x minus 3 being less than a quantity, then I would work my way through that and I would simplify. Okay? So continue to simplify until you can see what your radius is, until you have x minus a isolated. So right now what I know is that my radius of convergence has to be 1. In this case, my radius has to be 1. So my radius of convergence is equal to 1. So the radius is equal to 1. So now what I have to do is figure out, well, what is my interval of convergence? And I'm going to come back up here to my number line, or I could even use the absolute value, so x minus 3/4 being less than 1. I can use the number line, or I can use the absolute value. So that means x minus 3/4 in absolute value, if that's less than 1, that means it has to be less than 1 and also greater than -1. So that means that x is less than 7, add 3/4 to both sides, not equal to, or -1/4. Okay, so those are my two endpoints right there. Those are my two endpoints that I'm going to have to test. But if I go back to my visual here too as well, if I think about, okay, my radius of convergence was 1, so if I add 1 here, I end up at this endpoint 7/4, and if I subtract 1, I would end up at this endpoint, which is -1/4. So I know that I have convergence for everything in between. So right now my potential interval of convergence, so my interval of convergence has to be between -1/4 and 7/4. The only thing I don't know yet is if I should put a bracket or a parenthesis. Should I include those endpoints, or are they diverging? Are we diverging at the endpoint? So I'll put a little question mark right here. I still have to test those endpoints. So that's the last step. So now let's actually test the endpoints and see what we end up with. So notice when I test the endpoint, so let's start with x equals -1/4. When I test that endpoint and I plug that back into my original series, so right there's the original series up at the top. If I plug in -1/4 for x, what my series becomes is k equals 1 to infinity. When I plug in just looking at my highlight up there at the top, when I plug in -1/4 right there, I would get -1. 4 times -1/4, so I get -1 minus 3, so I get -4 to the k over k times 4 to the k when I plug in -1/4. Well, that just simplifies down to, because this becomes -1, let's change the color there, that becomes -1 1 to the k times 4 to the k. And so the 4k's cancel, and this becomes just negative 1 to the k over k, from k equals 1 to infinity. Now, we could apply the alternating series test to that, but this is absolutely a series we have dealt with multiple times. And so what you can do right here is you can say this is just the alternating harmonic series, which we have proved converges. It converges with the switch. It converges by the alternating series test. So we actually have convergence. So this endpoint converges. It is conditional. Okay, so just I will put that in parentheses. At those endpoints, it's often that we have conditional convergence, but we do have convergence. So let's come back up here to our interval of convergence and say, all right, we've got convergence. I can make that black. That is going to converge at negative 1, 4. All right, let's see if we get convergence at 7 fourths. So when I plug in x equals 7 fourths, when I plug that into the series, and again, just to remind us, I know it's off the page now, but off the screen, but the series itself was 4x minus 3 to the k. So when I plug in 7 fourths right there, I would get 7 minus 3. I get just 4 to the k. So I get 4 to the k over k times 4 to the k, from k equals 1 to infinity. Well, of course, the 4 to the k's cancel, and this leaves me just with 1 over k, from k equals 1 to infinity. But once again, this is one that we have seen a lot. This is a p series, but a very specific p series. This is the harmonic series. Okay? This is, you could say, harmonic, however you want to justify this, but this is the harmonic series or the p series, p equals 1, but either way, this diverges. However you want to justify it, if you want to actually just say that's the harmonic series or call it the p series, p equals 1, this diverges. This absolutely will be diverging. And so, therefore, we have divergence. We cannot include this point. This is diverges. It diverges at that endpoint. So when we come back to our interval of convergence right here, we would say, okay, this at 7 fourths, we have to leave the interval of convergence open because we have divergence at 7 fourths. So our radius of convergence is equal to 1. So to summarize everything that we've done here on this example, our radius of convergence is equal to 1, but our interval of convergence is from negative 1/4 to 7 fourths, including negative 1/4, but not including 7 fourths, open at 7 fourths. So back to this little graph that we have up here, we can put a bracket at negative 1/4 and a parenthesis at 7 fourths because we can include negative 1/4, but we cannot include 7 fourths. So our radius of convergence was 1, and our interval of convergence was between negative 1/4 to 7 fourths. Now, I know that was a long video, but I really wanted to get all 3 of those examples in so you could see more examples of how to do convergence of power series. I'm going to go ahead and make that a little bit one last screenshot here if you want to see that whole example. So again, figuring out where you're centered at, applying root or ratio tests to figure out the radius of convergence, and then testing endpoints. If you have a finite radius of convergence, then test your endpoints to see if you have convergence or divergence at the endpoints for that interval of convergence.